Welcome to the deep dive. Usually when we sit down to unpack the news, we are looking at the next step in a predictable sequence. A faster processor, a more efficient battery, a slightly better understanding of a known phenomena.
It's iterative.
It's iterative, it's safe. But today, we are not looking at an evolution. We are looking at a fracture. We are talking about a discovery reported yesterday, January 23, 2026, by Above the Norm News under the headline, "Scientists Discover Impossible Matter That Defies Known Physics."
And for once, the word impossible isn't just editorial hyperbole. It's a precise technical description of the conflict between what was observed in the laboratory and what the laws of physics, well, what they say is allowed to happen.
Exactly. And I think that is the most important place for us to start. This isn't science fiction. This isn't some theoretical model scribbled on a blackboard or a what-if scenario.
Oh, this is hard data.
This is a hard, data-driven crisis happening right now in a laboratory in Austria. We are looking at a state of matter that, according to the standard model of condensed matter physics, the rulebook we use to build everything from smartphones to MRI machines simply cannot exist.
That is the crux of it. We're staring at a direct violation of the rules we've relied on for decades. The researchers at TU Wien, along with a massive international team, including some key theorists from Rice University, have observed something in a crystal called CRU4SN6 that just shouldn't be there.
And they published it. It's not some preprint. This is peer-reviewed.
Peer-reviewed in Nature Physics. The paper is titled Emergent Topological Semimetal from Quantum Criticality. And that title, while it sounds dense and academic to a physicist, it's essentially a scream of confusion and excitement all at once.
So our mission today is clear. We are going to take this breaking news report from Above the Norm News, which frames this whole thing as a startling find, and we're going to cross-reference it directly with the raw data, the charts, the methodology from that Nature Physics paper.
Right. We need to see if the hype matches the data.
We need to understand the scale of this shock.
Yeah.
Because if this holds up, we aren't just looking at a new material to play with, are we?
No, not at all. If this result is confirmed and it holds up to scrutiny, we are looking at a breakdown of the rules that govern how matter organizes itself at the quantum level. Specifically, and this is the big one, it challenges the very existence of the quasi-particle.
The quasi-particle. I have a feeling we're going to be spending a lot of time on that word today.
We have to. It's the fundamental concept used to describe electrons in solids. If that concept breaks, we have to rewrite the textbook.
It's the bedrock.
It's the bedrock of modern electronics, of material science. If the bedrock is cracking, the whole building is at risk.
Okay, let's get into the evidence. This is an Above the Norm News deep dive, so we're stripping away the noise and looking right at the smoking gun. What did they see? What exactly triggered this alarm?
Okay, so to understand the anomaly, you first have to understand the setting. This didn't happen on a desktop at room temperature.
No, this is happening at the extremes.
The absolute extremes. The material is a compound of cerium, ruthenium, and tin CRU4SN6, a fairly complex intermetallic compound.
And the structure of that compound is critical here, isn't it? The paper makes a really big deal about its non-centrosymmetric tetragonal structure. Can we break that down for the listeners?
We can. Non-centrosymmetric is a mouthful, but it just means the crystal structure lacks a center of inversion.
Okay, what does that mean in simple terms?
Think of it this way. If you took the crystal and you imagined flipping it through a central point, like turning it inside out, it wouldn't look the same. It lacks that specific kind of symmetry.
Like my left hand and my right hand. They're mirror images, but you can't superimpose them. They lack that inversion symmetry.
That's a great way to put it. And that lack of symmetry is crucial because it's a prerequisite. It allows for certain exotic electronic behaviors to happen in the first place. But the structure alone isn't the surprise. We have plenty of non-centrosymmetric materials. The real surprise is what happens when you freeze it.
And we're talking cold.
We are talking colder than deep space. The experiments were conducted at fractions of a degree above absolute zero.
So below 1 Kelvin, that's what, negative 272 degrees Celsius?
Colder than that even, millikelvin temperatures. We're talking thousandths of a degree above the coldest possible temperature in the universe.
Why? Why go that low? Why not test it at room temperature?
Because heat is noise. At room temperature, atoms are jiggling around, vibrating like crazy. It's chaos.
Yeah.
If you want to see the fundamental quantum skeleton of the universe, you have to freeze out all that thermal noise.
You have to quiet the storm.
You have to quiet the storm so you can hear the whispers. You want to see what the electrons are doing when they're left to their own devices, governed only by quantum mechanics, not thermal mechanics.
So they freeze this crystal, CF4SN6 down to near absolute zero. It's sitting there in the dark and the cold. And then the above the norm news article says they saw a spontaneous voltage. Let's verify that with the paper. What does the data actually say?
Verified. The paper reports a spontaneous Hall effect. Now, normally the Hall effect is something every first-year physics student learns. You run a current through a material, say a strip of metal. Then you apply a magnetic field perpendicular to that current.
Right. And the magnet pushes the electrons to one side.
Exactly. The magnetic field exerts what's called a Lorentz force, and it curves the path of the electrons. They pile up on one side of the strip, and that pile-up creates a voltage you can measure across the material. That's the Hall voltage.
The key phrase there, and I want to really stress this for everyone listening, is apply a magnetic field.
It's the most important part of the definition. You need a magnet to push the electrons. But in this experiment, and this is the absolute core of the discovery, there was no applied magnetic field.
They didn't turn the magnet on.
There was no magnet to turn on. At that moment, it wasn't part of the equation. And yet, the material generated a distinct linear voltage across its surface.
So the electrons are curving.
The electrons were curving. They were moving in a specific, organized way, as if they were being driven by a ghost magnetic field, a field that was being generated by the material itself.
And the article, the ATN article, calls this the smoking gun of topological properties.
It is, 100%. Specifically, it's the signature of something called Weil nodes.
Okay, Weil nodes. What are those?
You can imagine them as little magnetic monopoles or knots in the electronic structure of the material. They're not real magnetic monopoles in space, but they exist in the material's momentum space. They act like points of intense localized magnetic fields.
So when electrons move through the material,
When they move through and pass near one of these Weil nodes, they get deflected, just as if a real powerful magnet were sitting right there. That deflection is what creates the spontaneous voltage. So seeing this effect tells us one thing for sure. Okay, this material is topological. It has these Weil nodes.
okay, so they found a topological material. We found those before.
Yeah.
I mean, the Nobel Prize in 2016 was awarded for this very field. We have topological insulators, topological semimetals. So why is the above the norm headline screaming impossible? Why were the researchers, as the article puts it, struggling to reconcile experimental reality with theory?
Right.
If it's just a knot in the electron structure, what's the big deal? What's the problem?
This is where we get to the heart of it. This brings us to section 2 of our investigation, the violation. To explain why this is impossible, I have to explain the quasi-particle.
The Lego brick.
Essentially, yes. In standard physics, what we call Fermi liquid theory, we treat electrons in a solid as if they're individual particles. Now, in reality, inside a metal, electrons are a swarm. It's a mosh pit. They are constantly pushing and repelling each other through electromagnetic forces. It's incredibly chaotic.
But Fermi liquid theory gives us a way to simplify that chaos.
Miraculously, yes. It lets us mathematically bundle up all those complex interactions and treat the electron as if it's still an individual particle. We just say it has a slightly different mass, an effective mass. We've effectively incorporated all that pushing and shoving into the weight of the particle.
And we call these modified electrons quasi-particles.
Correct. They're the actors on the stage. They're not the bare electrons of empty space, but they're the effective particles that carry charge and heat inside a material.
And the rule is, to have a play, you need actors.
Precisely. Standard theory dictates that topological states, these Weil nodes, these knots in the wave function, are properties of the quasiparticles. The knots are tied in the rope that is the electron's identity.
If you don't have the rope, you can't have the knot.
You cannot tie a knot in empty space. It's a property of the thing itself.
And CF4SN6, it doesn't have the rope.
It shouldn't. And this is where the term quantum critical point from the paper's title becomes so devastatingly important. The paper explicitly states that this material, CF4SN6, sits naturally at a quantum critical point, or a QCP.
Define that for us. What is a quantum critical point?
It's a point of maximum instability. Think of a phase transition, like water turning to ice. That happens at a specific temperature. A quantum phase transition happens at absolute zero, and it's driven not by temperature, but by some other parameter, like pressure or a magnetic field. A quantum critical point is the tipping point of that transition.
So it's a point of ultimate fragility.
Yes, and at this point, the quantum fluctuations, the inherent jitters of the universe itself, become so violent and so correlated over long distances that the electrons lose their individual individual identity. They stop acting like particles.
They dissolve.
They dissolve into a collective quantum soup. We call this a breakdown of the quasi-particle picture. The paper uses a more specific term for this material, condo destruction, which refers to the magnetic glue holding the electron's identity together, literally melting away.
I want to make sure I'm capturing the weight of this. The above the norm article says the electrons entered a non-Fermi liquid state where normal rules break down. You're saying that in this state, the particle effectively dies.
It ceases to be a useful concept. The very idea of an individual electron with a defined mass and charge moving through the lattice, it's gone. It's just a collective, entangled sea of charge.
They just measured the knot.
Yeah.
They measured the spontaneous Hall effect, which you said proves that topology exists.
Exactly. That is the paradox. That's the impossible part. They are holding a material that, by all definitions, is in a state of quantum critical chaos where particles do not exist, and yet they are observing a property topology that requires precise order and particle definition to exist.
It's like finding a perfectly preserved architectural blueprint inside a building that is already burned to ash.
That is a perfect analogy. The building, the particles is gone. It's ash. It's a quantum soup. But the blueprint, the topology, is somehow still there, hovering in the smoke. The paper validates this contradiction from every angle. They measured a spontaneous Hall conductivity that was linear and intrinsic. It was real.
And it was happening exactly where the quasi-particles should be dead.
Right at the point of maximum destruction.
The paper also mentions the magnitude of this effect. It says it was roughly 100 times larger than theoretical predictions for ordinary topological semimetals. What does that tell us?
It tells us this isn't some weak leftover effect. If this were a tiny, barely detectable signal, you might try to dismiss it as noise or maybe an effect from some small impurity in the crystal.
But 100 times larger.
A signal 100 times larger than standard theory predicts. That screams that something new and fundamental is driving it. It suggests that the very mechanism creating this voltage is turbocharged by the critical state. The chaos isn't a problem for the effect. It seems to be the engine for the effect.
Now, you said ordinary topological semimetals. The paper does draw a comparison to another material, doesn't it? C3x4PD3.
It does, and that's a key point of comparison. That material, C3x4PD3, is what's called a well-condo semimetal. It also shows a giant topological response. But, and this is the crucial difference, it's a stable material, it's a well-behaved Fermi liquid, the quasi-particles are alive and well.
So in that material, the rope and the knot both exist. It makes sense. It follows the rules.
It follows the rules. C4SN6, our material, is different. It's critical, it's unstable, and it's that inherent instability, that non-Fermi liquid character that makes this finding so impossible under our current models. It has the knot, but no rope.
Okay, so we have a smoking gun observation that contradicts the fundamental theory of how matter is built. The researchers didn't just accept this paradox, though. They decided to interrogate the material. This brings us to Section 3. The investigation. They didn't just look at it. The paper describes an intense regimen of tuning the system.
Interrogation is exactly the right word. They tortured this crystal. To really understand what was happening, they needed to see if they could turn the effect on and off. They needed to control it.
How do you do that?
You apply pressure. Hydrostatic pressure. They squeeze the crystal with immense force, up to 24,000 atmospheres or 24 kilobars.
24,000 times the pressure of the air we're breathing right now.
Yes.
Yeah.
You're essentially crushing the atomic lattice, forcing the atoms closer together to see how the electronic state responds. And at the same time, they also applied magnetic fields.
And the goal of all this squeezing and magnetizing was what?
To move the material away from that quantum critical point.
Yeah.
Remember, the QCP is a specific tipping point. By applying pressure or a magnetic field, you can push the system off that point. You can tune it away from the chaos.
So they wanted to see, if we restore order, if we force the quasi-particles to come back to life by moving away from the chaos, what happens to the topology? Logic would suggest that if the topology depends on the particles, then bringing the particles back should make the topological signal stronger, more stable.
That is the logical assumption. That's what any physicist would have predicted going into this experiment. If the particles are the rope and you fix the frayed rope, the knot should become tighter and more well-defined.
And this investigation resulted in what the paper calls the phase diagram. For listeners, you can imagine this as a map of the material's behavior under different conditions of pressure and magnetic field. And on this map, the researchers found a dome.
The dome structure is the visual evidence of the crime. It's the centerpiece of the paper. What they found was that the topological effect, that spontaneous voltage, forms a dome in the phase diagram. And the peak of that dome, the highest point where the effect is strongest, is exactly at zero pressure and zero magnetic field.
Which is the quantum critical point.
Yes. The impossible behavior peaks exactly where the quantum criticality is maximized, at the heart of the chaos.
And what happened when they applied pressure, when they moved away from that point?
As they applied pressure or as they applied magnetic fields, they moved away from the critical point. They were effectively calming the storm, suppressing the quantum fluctuations, and restoring the quasiparticles. The material was becoming a more normal metal.
And the impossible effect, the spontaneous voltage.
It weakened, it died away. As they moved down the sides of the dome away from the peak, the signal got smaller and smaller until it vanished.
So, let me get this straight. As they restored the rope, the knot disappeared.
That's what the data says. It's completely counterintuitive. It's the opposite of what we expected. You'd think that as you restore the particles, the topology, which supposedly relies on particles, would get stronger. But the data is unequivocal.
Is there other evidence in the paper that they were actually restoring the particles?
Yes, absolutely. They measured something called the Weyl velocity, which is related to the speed of the electrons in this topological state. As they increased pressure, the Weyl velocity increased. This is a clear sign that the system was moving away from the highly correlated, sluggish critical state. It was becoming a more conventional, weakly interacting metal again.
And as it became normal, the unique topological signature vanished.
It vanished, so the conclusion is inescapable. The chaos isn't destroying the topology. The chaos is creating it.
Or, as the paper suggests, the quantum criticality is actually stabilizing the state. It defies the expectation that chaos destroys order. Here, the extreme fluctuations of the critical point seem to be the very fuel that sustains this bizarre topological state. The above-norm news article gets a little poetic here, and I want to see if you think this framing is justified by the data. They write, the topological phase emerges from the quantum critical fluctuations like a phoenix rising from flames.
You know, for a news headline, it's dramatic, but scientifically. It's surprisingly accurate. The flames are the quantum critical fluctuations, the Kondo destruction, the death of the particle identity. The phoenix is this wild Kondo state, this emergent topology. And the data shows they are inextricably linked. You cannot have one without the other in this material. The topology is born from the death of the particle.
This leads us to the inevitable question, the one that must have kept them up at night. How? How is this possible? If the Lego bricks are gone, what is building the structure?
Right.
The researchers didn't just leave it as a mystery. They brought in theorists, specifically that collaboration with Rice University we mentioned. And this brings us to Section 4, the theoretical rescue.
This is the heavy lifting part of the paper where they try to build a new framework to explain the impossible. The experimentalists said, look at this impossible thing, and the theorists had to answer the question, how do you describe topology without particles?
And what was their answer? If it's not particles, what is it?
It's symmetry.
Symmetry. Sounds abstract.
It is abstract, but it's also more fundamental than particles. The paper argues that even when the quasi-particles are destroyed, even when the electron soup is chaotic and undefined, the underlying symmetries of the crystal lattice remain. The crystal itself still has a shape. It still has rules about how things can move through it based on its non-centrosymmetric geometry. It has global constraints that don't depend on the existence of individual particles.
So the building might be burned to ash, the bricks might have melted, but the foundation, the concrete footprint on the ground, is still there.
Exactly, and that footprint forces the ghosts of the electrons to behave in a certain way. The technical term the paper uses is single particle spectral functions. You can think of these as the mathematical probability maps of where an electron could be. The particle itself is gone, ill-defined, but its spectral footprint remains.
And these ghosts are forced to obey the rules of the house.
Yes. The symmetry constraints of the crystal are so robust that they force these spectral functions, these ghosts, to cross each other at specific points in momentum space. And these enforced crossings are the Weyl nodes.
So the knot isn't being tied in a rope anymore. The knot is being forced into existence by the shape of the box.
That's a fantastic way to put it. The symmetry of the space itself, combined with the intense quantum fluctuations, forces the knot to exist, with or without a well-defined rope to tie it in.
The verdict from the paper, I think it's worth quoting directly, is genuine topology can exist in quantum critical metals.
And that sentence, it sounds simple, but it's revolutionary. It requires us to abandon the particle picture entirely for these systems. We have to stop thinking of matter as being made of little balls bouncing around and start thinking of matter as a manifestation of symmetry and fluctuation.
The symmetry is the primary reality.
The particle was just a temporary low-energy vessel for that symmetry.
I see this tension here between the above the norm article and the paper. The ATN article emphasizes the mystery, the idea that this defies physics, but the paper emphasizes the robustness of symmetry.
And they're both right. They're two sides of the same coin. It is a mystery because our intuition is so deeply ingrained with the particle model, it defies known physics specifically. It defies Fermi liquid theory. But the paper is providing the solution to the mystery. It's saying, look deeper. When you look deeper, you realize that symmetry is more fundamental than the particles themselves. Symmetry survives the fire.
I want to pivot now to section 5, because this connects to a broader and equally bizarre area of physics, so-called strange metals. The paper makes a direct comparison to superconductivity, which feels important for placing this discovery in the bigger picture.
Right. This is crucial for context. We've seen these domes of strange behavior near quantum critical points before, specifically in the field of unconventional superconductivity.
High-temperature superconductors.
Exactly. In many of those materials, you also see a dome shape. You tune the material towards a quantum critical point, and a dome of superconductivity appears.
Okay, so usually you have chaos at the critical point, and then this dome of superconductivity appears to save the day.
In a way, yes. Superconductivity is an ordered state. In that state, the system finds a way to escape the chaos of the critical point. Electrons form Cooper pairs, condense into a single quantum state, and they release entropy. They settle down. It's like the system creates a new, highly ordered state as a defense mechanism against the instability.
But N6 is different.
Radically different. In this new well-Kondo state, the system doesn't escape. It doesn't form Cooper pairs, doesn't settle down and become an ordered liquid. The paper is very clear that it remains a non-Fermi liquid throughout the topological dome.
It stays strange.
It stays strange even while being topological. There's no release of entropy. It doesn't try to cure the instability. It harnesses it. It lives in the chaos.
Let's clarify that term, strange metal. It sounds like something out of science fiction, but it's a real and very frustrating term in physics.
It is. A strange metal, or a non-Fermi liquid, is a state of matter where electrons just don't act like particles. The most famous signature is that its electrical resistance changes linearly with temperature, which shouldn't happen if charge is carried by individual quasiparticles. It suggests a state of maximal quantum entanglement,
where every electron is connected to every other electron.
in a deep, profound way. It's not a gas of particles anymore. It's a single, indivisible quantum fluid. And the implication here is that this material, CuRe4SN6, is a strange metal that is also topological. Two of the most bizarre quantum phenomena rolled into one.
Does the paper suggest ways to confirm just how strange it is?
It does. It explicitly calls for future tests, specifically to measure shot noise and entanglement.
What is shot noise?
Shot noise is the noise generated by the discrete nature of charge. Think of it like rain on a tin roof. Tick, tick, tick. Each tick is an individual raindrop, or in our case, an electron arriving. That's the sound of particles.
And if this is a strange metal?
If it's truly a non-Fermi liquid, the shot noise should be suppressed. It shouldn't sound like discrete raindrops. It should sound like a smooth, continuous stream of water from a hose.
Because there are no drops anymore. No particles, just the flow.
Exactly. If they measure that suppressed shot noise, it would be definitive proof that the electrons aren't arriving like individual entities, but as a continuous, entangled fluid.
This feels like we are getting closer and closer to understanding the fundamental fabric of reality. But let's ground this for a moment. Section 6. The so what? Why does this disrupt everything? The Above the Norm article makes a big claim. It says this could accelerate the race toward revolutionary electronics. Is that just hype, or is it real?
It's real, but maybe not in the way people might immediately think. It's not about putting a tiny piece of CuRe4SN6 into your iPhone tomorrow. This material only works at near absolute zero.
Right. So what is it about?
It's about a new design principle.
Explain that.
For the last 70 years, materials science has been about finding stable materials. We look for things that are solid, predictable, well-behaved. We actively avoid the chaos. We run away from quantum critical points because they are messy, unstable, and hard to control.
You don't build a house on quicksand.
Exactly. But this paper suggests we should be doing the opposite. It suggests we should be deliberately hunting for the quicksand. We should be looking for materials that are tuned to be right on the verge of falling apart, quantum mechanically speaking.
Because that's where the magic happens.
That is where the most exotic properties, like these incredibly robust topological states, emerge from the fluctuations. If we can learn to control and harness this instability, we could design entirely new classes of devices.
Like what? What are the potential applications?
Well, low-power transistors, from one, spintronics. But the big one is quantum computing.
How does this help quantum computing?
One of the biggest problems in quantum computing is decoherence. Qubits are incredibly fragile. A stray vibration or a change in temperature can destroy the quantum information. But these topological states, these whale nodes, are different. Because they are protected by symmetry, they are incredibly robust against noise.
Which is deeply ironic because they are born from noise.
It's the ultimate paradox. They are stable because they are born from the ultimate instability. You could potentially use one of these topological knots to store a qubit of information. And because the knot is tied by the fundamental symmetry of the universe itself, it's very, very hard to accidentally untie. You could build a naturally fault-tolerant quantum computer.
And the scientific impact, beyond the gadgets.
It forces a fundamental shift in worldview. We have to stop thinking of matter as just Lego bricks. We have to start thinking in terms of symmetries and fluctuations. If this result holds globally, and the paper suggests this mechanism is likely general, not just a one-off fluke in this single compound, it validates this idea of Kondo destruction as a universal way to create new states of matter.
It gives us a new treasure map.
It gives us a new treasure map, and it tells us the treasure is buried where we always thought there were just monsters. It opens a new search strategy for materials that, under the old rules, we would have considered impossible and not even bothered to look for.
We're looking for the ghosts in the machine, and we're finding out the ghosts might be more real than the machine itself.
That's a haunting way to put it, but yes. We are realizing that the machine, the particle, might just be a low-energy illusion. The high-energy reality, the fundamental reality, might be the ghost. The symmetry.
We've covered the breaking news aspect, the raw data of the spontaneous Hall effect, the investigation that revealed the dome in the phase diagram, and the theoretical rescue that places symmetry above particles. As we wrap up this deep dive, let's just summarize the investigation one last time.
The impossible matter is real. Sierra 4SN6 proves, with very strong evidence, that topology can survive the destruction of particles. The above-the-norm report, while it sounds sensational, actually aligns perfectly with the core findings of the Nature Physics paper. We are looking at a break in the standard model of condensed matter. We are looking at the discovery of a state where symmetry, not particles, dictates reality.
We usually end these deep dives with a key takeaway, but this one feels bigger than that, more fundamental.
It is. It's a shift in how we perceive the very ground beneath our feet.
And so I want to leave our listeners with this final thought. We spend our lives interacting with things, solid objects. We think of the universe as a collection of stuff, of particles, but this discovery implies that the stuff is secondary. The stuff can dissolve into chaos, into a quantum soup of near-nothingness. But the symmetry, the mathematical rule of the shape of space remains, and that symmetry can force order, intricate and robust order, out of that absolute chaos.
If symmetry is the only thing that survives the fire, if it's the one thing that remains when particles themselves die, what does that say about the fundamental structure of the universe? Are particles just an illusion? A convenient story we tell ourselves? Is symmetry the only real thing?
Something to mull over. This has been an Above the Norm News Deep Dive. We will have more Above the Norm News Deep Dives very soon, so please subscribe to our channel.
Stay curious.
And stay critical. See you next time.